So when a computer talks in a network, it leaves behind a fingerprint, tiny digital clues about its identity, and there are tools designed to read that. Now this is a Raspberry Pi. It has never run a single line of Windows code. However, if we look at this, you will see it's been detected as a Windows 2012 R2 server. This is a lie. The question is, how do you teach a tiny computer to lie so perfectly that it fools the experts, and why would you want to? Hey Pixelers, Michael Haddon here, and every second corporate networks are fighting this silent war, where the first stage is reconnaissance, it's stealthy, it's quiet, it's someone getting into your network and feeling their way around to figure out everything you have within your system. They're constantly probing, looking for targets to jump onto the next node in like some sort of traversal attack, trying to move horizontally through your system until they can find a way to go even deeper. They're looking for an easy way in, but what happens when that doorknob rattle comes from someone who's already passed the first door?
Yeah, back in the day, I was working at my own company, Fleetbird, and we had lots of cloud security because everything was in the cloud. Everything was AWS. And we have lots of security there, but almost no local security. So everybody could just, walk into our office. So it's the best time to attack, like New Year's Eve and Christmas, absolute classic. So yeah, lots of people are attacking, little people are available. So we were just deciding, hey, what happens if somebody would be in our office already or in the network already? We would not be able to detect it. They have all the time in the world when we're back from holidays to see if there's actually, some valuable data there.
Yeah, if you look like you belong somewhere, it's easy to walk in without being questioned, and at the end of the day, all of your staff isn't necessarily trained to weed out bad actors.
Exactly. In our case, we have lots of customers coming in for just meetings or checking out devices or talking to the salespeople, and they would just come there, they would ring the doorbell or knock, somebody would open the door. And at a certain point, you have so many employees, nobody knows everybody. So you can just go in. And I was thinking, maybe I can just implement a quick solution. And I started Googling. There was nothing simple to implement like plug and play. The task, of course, can be big or small, depending on how much time you want to invest. And me as a CTO at this point in time, I wanted to go and invest as little time as possible and get the max security out.
But what is your opinion on using a SIEM? I know they can sometimes cost hundreds or thousands per month, but if you use a third-party one, they don't take that long to set up, do they?
Yeah, so using a Honeypot is much cheaper, for example, than using a SIEM, because a SIEM will collect every event from every different computer on the network. And it's, of course, lots of data which has to be stored for a long time. And then you have to go through the data and trying to figure out if it's actually alert or not.
All right, so the challenge is clear. Let's not try and build another system that just creates noise. If there's any sort of trip in the system, then I guess it must be something serious, right?
For the SentryBox, there are simply no false alerts. If somebody interacts with the SentryBox, it's definitely an alert.
So since security is our main concern here, I guess we want to have something which can run inside of the user's network rather than having to send data off to our external servers. Is that correct?
That's absolutely correct. You can manage the SentryBoxes by yourself in your internal network, and they will just distribute all the alerts they find within the local network. So there's no need for internet connection.
So to pull this off, our Raspberry Pi has to become a method actor, has to assume the role and try to become a Windows server with how it handles networking internally. As Benjamin calls it, a SentryBox. We will start with easy stuff like a fake web page and changing the MAC address and any sort of easy sysctl things we can do. But let's try to see if we can dive into the networking stack with eBPF and fundamentally change how it behaves. I have here a Raspberry Pi Compute Module 5 with a baseboard from Waveshare. It gives me 2 Ethernet ports, a charging USB-C port, and a USB-A port. I'm going to install Ubuntu 25.04 on it. This is going to ensure I have the latest version of the Linux kernel, which is going to allow me to use the latest Linux Traffic Control TCX implementation in the kernel, which I think is from Linux 6.6, I think. You see, every device you will have a slightly different networking stack. Some are built on fundamentally different technologies, some have tiny little deviations in time, and it's these minute differences between your different devices that creates that fingerprint. Especially if not all of your devices are currently updated to the latest versions and they're not all literally on the same uniform operating system and everything like that. So they're all giving off very tiny signatures of what they are. For example, with time to live, think of it as the expiration date of your packet. On a Linux device, it usually defaults to around 64, and on a Windows server, it usually defaults to around 128. So if you have a networking scanning tool and you just see the time to live on packets, you're instantly given some information about whether or not this is a Linux device or a Windows device, probably. Another is how it behaves when you knock on the wrong door, right? When you try to access a port which doesn't have anything exposed on it. On a Linux device, it will just say, go away, right? On a Windows device, it will say, go away, but I acknowledged that you knocked on my door, which seems like a very small difference, but once again, it's these minute differences that create the fingerprint, just like how all fingers kind of look the same, but then there's very tiny notches in how the actual fingerprint evolved, which means that it's easy to detect one person from another. And another good example is when Microsoft released Windows Vista, they fundamentally rewrote their entire networking stack, meaning that devices pre-Vista and post-Vista have a fundamentally different signature, which makes it really obvious to be able to detect which one's which. So we can think of this like an accent. You're still speaking the same language for fundamental networking, right? But there's tiny differences in how things are pronounced. And so we have to try to make this pronounce its networking just like Windows does, which isn't going to be easy because this is fundamentally woven into how the kernel operates. Some things, like time to live, can be overridden quite easily by just saying to the systemctl, hey, why don't we just use a different time to live? But for the fundamental way the networking works, we're going to have to try and change its perceived behavior. So this is our starting situation. And as you can see, it says Linux 5.3, 5.4, 5.x. That's not entirely true. We're actually on Linux 6.x. But the reason why it's probably not getting it entirely accurate, this is the fingerprint, by the way. The reason why it's not getting it entirely accurate is probably because we don't have enough stuff running on that device to make it more obvious. So you can see we have SSH running on that device, but there's nothing else that it can detect. And so if there were more things running on the device, Nmap has more ports to scan over to understand and to extract more of a fingerprint from, to get a more accurate answer as to what we're running. So as you can see, it's already getting a good understanding of what's going on. So I've been working on this for a while. I have this new Vagrant set up so I can test it more locally, so it's, faster deployments, and I don't have to worry about locking myself out of the Raspberry Pi, which kept happening. Unfortunately, I can't seem to be able to detect what operating system it is, so I've done something. It's like permanently messed up the networking, so it's detecting nothing. So it doesn't seem to. All it knows is because I gave it a different MAC address that it's probably a VMware thing, even though I'm using libvirt. But other than that, it is pretty stuck. So let's see if we can make a bit more progress and actually get somewhere. Alright, so I've been making quite a bit of progress. The difficulty is you have to keep re-verifying the information to ensure the verifier for eBPF doesn't get upset. So that's been the most difficult part, constantly trying to make the verifier happy because we keep mutating the networking stack. And so the verifier can't understand, this is the eBPF verifier, if we have null references or not, even if we've already checked something. So you're constantly rechecking, and that's been the most difficult part. But the good news is it now detects Windows 10. It's not Windows Server 2012, what we want. We're making progress. It's not entirely there, but this is a good start. At least now we have a chance of making this think it's Windows, which is a good first step, I think. Hey, Benjamin. We got some progress. It says it's a Windows device, but unfortunately, I can't seem to be able to connect to the HTTP server, so I might have accidentally fully buggered the networking.
That's good, but it's absolutely crucial that the network is working on a good honeypot. Otherwise, the hackers cannot interact with all the different services, and it doesn't look like a real device.
So I think I know what's going wrong. When we respond to the Nmap scanner with our spoofed networking information and packets and all of this, that all works, but obviously Nmap is going to want to connect back based on that information we've given it. And that we can't just lie one way, because if they then respond to our lie, our internal kernel can't understand the message because it never produced that message to begin with. So we have to lie both ways. We have to maintain the lie that we send from our Raspberry Pi to the Nmap scanner. And then when the Nmap scanner responds to the Raspberry Pi, we then have to lie to its own kernel, so then it can maintain the sequence of messages. So as they say, the hardest part of telling a lie is maintaining the lie, right? So we're going to have to record this information inside of the eBPF application to be able to map it back. So the good thing is eBPF lets you do this with maps, but this is going to be complicated because we're going to have to keep track of that map to be able to keep track of the conversation and, like I said, the lie. So an example is the initial sequence number, or ISN. It's like a unique serial number for the start of every TCP conversation. A Linux machine and a Windows machine fundamentally generate them differently, right? So as you can see here with Linux, they're large numbers with huge unpredictable jumps between the numbers. And Windows, while it still has unpredictable jumps, they're much smaller, more like a steady climb. And Nmap is specifically trained to be able to spot this difference in rhythm. It makes multiple connections and it detects the rhythm of these numbers. If our Pi sends out a package with that chaotic Linux-style numbering, the disguise is instantly blown, right? So we have to produce numbers which seem like Windows. So we have to lie. Our eBPF program doesn't just change one number, it has to create an entirely new rhythm, a Windows rhythm which it maintains across multiple connections so that Nmap thinks that this is the rhythm that it's been given. And we have to record that rhythm to be consistent with it. So we have to intercept the kernel's chaotic numbers that it produces with our own carefully crafted rhythm that follows a more steady pattern of the Windows server. But the problem is when the reply comes back to our own kernel, it's expecting its own chaotic number, right? It doesn't expect the Windows number we've given out to Nmap. So we have to then transform that back into our original Linux number to convince the Linux kernel that this was a consistent, coherent conversation. Oh god. Alright, so I've tried to implement these states so we can maintain this lie. And if we look here, I have a response, and I guess it's a moment of truth, but we have a 94% guess that it's a Microsoft Windows 2012, 2022, 7. So it's a bit broad. It's not isolated it exactly. We see some Linux kernels coming up here. But it does have our Tiger operating system, Windows Server, 2012 R2 at 94%. So this is good progress. And now if you look at this, I can successfully connect to the HTTP server. So we have networking working. We've maintained the lie, so to speak. Okay, so this is going to be the moment of truth. Let's see if we can load it onto this device. So we can actually have on our Raspberry Pi our eBPF faker, spoofer, chameleon, SentryBox system. So Benjamin, check this out. 92% on the actual Raspberry Pi is what it's saying it is for Microsoft Windows 2012, and we have R2 here. And also, interestingly, on the actual device, we don't see any guesses about Linux at all. It's purely guessing Windows, as it seems. So we've, to a certain extent, at least successfully spoofed it that it's definitely a Windows device.
Wow, we can even connect to the HTTP server and see the IIS default page.
Yeah, so I think we could probably push it past 92%, but I think the reason why it's still down at 92% is I think I got some tweaking to the TCP options, but I think my ISN numbers are still not coming back perfectly. I've not quite precisely figured out the rhythm. And obviously this device has a different clock speed. I was tempted to actually try and reinstall the kernel, because then I could change the actual fundamental clock speed of the kernel, I believe. But I thought that was a bridge too far and unnecessary if we could get practically there anyway.
Yeah, so it's basically like an interactive honeypot, and it looks exactly like other systems which are already on the network. And if an attacker comes and wants to hack your network, he will scan everything and also interact with the SentryBox, which will look exactly like your router, for example. And then we know somebody's there. So we are able to detect if somebody's moving through the network from computer to computer.
Yeah, that's incredible. And we've laid the foundation. And just before I spend another week arguing with the Linux kernel about timestamps, what's the full version? Where do we go from here?
Yeah, I will tell you everything about it. Just in the short term. If you have like a typical device on the network, it will have different services it provides. For example, if you have a router, it will provide an admin dashboard via HTTP to log into, so you can actually configure the router. And we're kind of emulating those type of services, but we're also emulating data storage services like FTP, for example. And if some hacker comes along and scans the network device, it will try to emulate also the fingerprint of the actual device. So this hacker on the screen will see, oh, that's actually a Cisco device or a Fritzbox or whatever device we're emulating.
Awesome. I've really loved working on this project with you, Benjamin. And if anyone has any questions, where do they go? Where do they go to reach out to you to learn more about this project?
If you want to learn more about deception or how to protect your network, visit SentryBox.io.
Well, there you go. We successfully turned this Linux Ubuntu device into a Windows device, or at least that's how Nmap sees it. I hope you guys found this really informative and you learned a lot. Please feel free to reach out to Benjamin if there's more you would like to know. And as always, I hope you guys have a lovely day and thank you very much for watching. Cheers.